Alright, so to solve this system of linear equations by Cramer's rule, let me remind you what we did yesterday. So for x, at the denominator we write it matrix for the left side. We just write the matrix for the left side of the equation, which is -1, 2, 2, -2. And at the numerator, we write the same matrix, but we replace the column for x by the column of coefficient. So here, the second column will remain same, which is 2, -2. But the first column will replace it by 7, -4. Now, if you solve this matrix, you will have your answer for x. And for y, denominator, we have the same denominator for y, which is -1, 2, 2, -2. But for x, for the numerator, we replace the column for y by the column of coefficient, which is, so the first column will remain same here, which is -1, 2. And the second column will be replaced by 7, -4. Now, if we solve these matrices, we'll be able to know the x and y's. Now, let's go back to x here. If you try to solve x, how you solve? You multiply 7 times -2 first, which is -14. Then negative sign, then 4 times -4 times 2, which is -8, so it will be -8 here. Bottom numerator denominator for x is -1 times -2, which is 2, negative sign, 2 times 2, which is 4, negative sign, 4. So here we have -2 in the denominator. Numerator we have -14 plus 8, which is -6. If we solve it, it will be 3. Do you have 3 for x? For y, since we have the same numerator, just let's write -2 here. This numerator will be -2. For numerator, we multiply -1 times -4, which becomes 4, and then we'll multiply. We have a negative sign, and we multiply 7 times 2, which is 14. Let's write 14 here. This becomes -10 minus -2, which is 5. We have the same answer. Now, this was what we did for the, solving the system of linear equations with 2 variables by Cramer's rule. So let's just look at one more step here. Now here you are looking at a bigger matrix, because yesterday we tried, up to yesterday we tried to solve the system of linear equation of 4 matrix, 2 by 2 matrix, 3 by 3 matrix. Now we have a 4 by 4 matrix here. Now, so today we'll be talking a little bit in the generic mode, that how in general you can address any matrix like this. Okay, so how you can basically solve any matrix, because first of all, solving matrix means you are trying to find the determinant of a matrix. Now we know how to do that, how to find the determinant of 2 by 2 matrix. And if you try to recall what we did when we tried to find the matrix for 3 by 3 matrix, we basically found the 3 by 3 determinant of 3 by 3 matrix in terms of 2 by 2 matrix. Now let us recall that slide. Then I'll show you what we did. Remember, every time whenever we try to find the determinant here, because when you are solving a system of linear equation with 3 unknowns, we had to find d, dx, dy, and dz. And all of these matrices were 3 by 3 matrices. Now to solve such matrices, what we did? We had to deal with a 3 by 3 matrix and find the determinant for those. If you go back and look at how we did that, let me remind you what we did. This was exactly what we did, because to solve a 3 by 3 to find a determinant for 3 by 3 matrix, all you do is we just write this equation with a matrix, and in this equation you see we are basically dealing with a 2 by 2 matrix in each of these. So generically, in general, we say that if we have a matrix of n order, now what do you mean by n order? Now here, these are the matrix of 3, order 3. So that's why they are called third order matrix. Now the one that we are talking about, that is a fourth order matrix, because it's a 4 by 4. So in general, we say that if we are trying to find the determinant of a n order matrix, we do it by n minus 1 order matrix, because the one that you are looking at here is there is 1 order less, right? Because when you are trying to find the determinant of 3 by 3 matrix, you are doing it by 2 by 2 matrix. Similarly, for an example, when you will be trying to find the determinant of a 4 by 4 matrix, you will be doing it just by a determinant of 3 by 3 matrix. It will be always true. So if it is a high order matrix, you will be always doing in this way. Okay. So let's go back to that 4 by 4 matrix, and this is the last topic we'll be covering from this section. So here again, see, this is a fourth order. So whatever the determinant we'll be finding, that will be a fourth order determinant, and we'll be solving and we'll be finding the determinant in order of by third order determinant. Okay. Now how to do that? And also you will find a lot of similarity between the steps we did for the 3 by 3 matrix. It's pretty similar to the 3 by 3 matrix, but the only difference is this. What do? We first write an element. Let's say, remember how we find the 3 by 3 matrix determinant. We just picked one element from first column and eliminated the column and row for that column, for element, and wrote the rest, multiplied with that coefficient. Let us do the same for this. Let's say this is our matrix here, 1, 2, 0, 0, 0, 1, negative 2, 0, 1, negative 2, 0, negative 1, negative 1, 3, 1, 1. If you are solving this, if you are trying to find the determinant of this matrix, we always want to have the determinant, because using Cramer's rule, when you are solving the system of linear equations of any number of variables, you will need the determinant. And then you have a straight formula by which you can bypass the regular row operations of matrices. Because you see, when you have a bigger matrix, the row operations will be more and more complex, because at the end you still want the row echelon form here, which will be along this line. Now let me give you the clue for this. Again, we'll be working with this column. So let's take the first element here from the column, so which is 1. When we take 1, what do you do? Remember, we are doing the same thing that we did before. We will eliminate this column and we will eliminate this row. So we are basically eliminating the column and row for that element, and then we'll write the rest multiplied with this. I just wrote the rest. Okay. Now next, I'll take this one, which is meaningless at this point because this is 0. If you take this, everything will be 0 because you are just multiplying everything by 0. But still, I want to write it just to make sure we understand how we do it. And also, in addition to that, another point we may want to know that, for each position in the matrix, doesn't matter how big it is or how, what order you have it for that, each position, you can assume that each position has a sign, okay? And the signs are like this. You will start from positive sign here, okay? So this is going to be the negative sign, and the next sign is going to be positive. Next sign is going to be negative. You always start from positive sign, positive, negative, positive, negative. That's how we think as for the position. Okay. So before 0, zero will be preceded by a negative sign. At this point, the 0 doesn't make sense because you are just multiplying the whole thing by 0, so it will be 0. But still, I just wanted to make sure that we understand how we do the calculation. So when we take the 0, again, we eliminate the column of the 0, and this time we will eliminate the row for the 0 as well. And we'll write the rest. So we are eliminating this one and this one. So the rest is here. So we are writing 2, 0, 0, and this one is -2, 0, -1, and the last one is 3, 1, 1. Still we are doing the same process. Now next one, you see here, this is positive here. So we will write +1, and then this time we eliminate the first column, third row. We eliminate the third row, and then we write the rest. So now we have 2, 0, 0 here, and then 1, -2, 0, 3, 1, 1. And then for the last element, now the sign is negative for the last element, but look at the last element. Last element itself is negative, so let's write the last element here. Because as I said, it's positive, negative, positive, negative. So it will be preceded by a negative sign, but itself, the last element itself is a negative number, so we just write that. And then now we eliminate the first column, fourth row. We'll write the rest of those elements. So we'll write 2, 0, 0, 1, -2, 0, and -2, 0, -1. Now, at this point, what is next? So this is so you will have your determinant from here. At this point, what is next? The next is, at this point we have all 3 third-order matrix here. Now for each third-order matrix, we know how to find the determinant, right? As I know that you can probably solve everything in your calculator, but at the same time, we just want to make sure that we understand how the calculations are being done. So for the first matrix here, since this itself is a third-order matrix, so how do we find the determinant for a third-order matrix? We'll just do the step that we had before for the third-order matrix. How we find the third-order matrix? We find the determinant of each third-order matrix in order of second-order matrix. So for each of those, let's pick the first one. So the first third-order matrix, at this point we have 4 matrices here. We probably can ignore this one because this is multiplied by 0, so you will not have anything here. So the first one is, let's write the first one and let's see what we do. So we'll take one third-order matrix at a time, and we'll try to solve that and show you how to 1, -2, 0, -2, 0, -1, 3, 1, 1. Now this is one of the third-order matrix. Now how we find the determinant for this one? What do? Just take the first column, first element, and then when we take the first element, we eliminate the first column, first row, right? So the rest is here, and we know how to work with this, right? So we just cross multiply, right? So 0 times 1 is 0, Negative 1 times 1 is negative 1, so again negative 1. Right? It's just the same way we did it yesterday. So negative 2. Then we eliminate first column, second row, multiply this 2. Negative 2 times 1, which is negative 2. Then this 2, which is 0. Last element here, which is 3. Since we are taking 3, we eliminate first column, last row. We just eliminate the column and row of that element, right? So first column, last row. So what we are taking is this 2 multiplied negative 2 times negative 1, which is 2. 0 times 0, 0. Now we have, here we have 1 times 1, which is 1. Positive 2 times negative 2, which is negative 8. We have 6 here. And then it's negative 1. So that's the determinant of this matrix. So that's how we know that, okay, determinant of this matrix is negative 1. Similarly, we can ignore probably this one. Let's ignore it because it's multiplied by 0, so it doesn't matter what you do. So similarly, we can find the determinant for this matrix and this matrix. Oh, it's a negative 4, I'm sorry. So 7 is negative 3, right? Oh, positive 3. 7, let me check it out. So 1 times 1, negative 4, positive 6. Okay, now this is 3, so let's write 3 here. This is 3. Okay, now let's do the same math for the other two matrices. We have two other 3 by 3 matrices. Let's erase this one, and the second matrix here is 2 0 0. I'm taking the last from the last row because the second matrix is gone because that's multiplied by 0, so we don't care about that. 1 negative 2 0 and 3 1 1. Now for this one, first element from first column, let's take 2. Multiply this 2, which is negative 2. Multiply this 2, which is 0. Middle element, which is 1. We eliminate the column 1, row 2. And 0 times 1 is 0. 0 times 1 is 0. So, and the last element is 3. We eliminate column 1, row 3. Multiply this 2, which is 0. Multiply this 2, which is 0. So here we have negative 4. I think everything else is 0, right? This is 0, this is 0. So this matrix is negative 4. We still have one more to go, which is the last one here. So let's write this one. So the first element is 2, negative 2 times negative 1, because we eliminate this row, this column, first row. 2 times negative 2 times negative 1, which is 2, minus 0, negative 1, 0 times negative 1, 0 times negative 1, so everything is 0 here. So this is positive 2, positive negative 2 times 0 times 0 here, 0 times negative 2, which is again 0 times 0. So everything is 0 here. We just have 4. So the last matrix is 4 here. Now, once we have the determinant of everything, it's just a simple equation of, so how we find it? So we have 1 times 3 minus 0. So let's ignore this one. This is 1 times, it was negative 4, right? Times negative 4 minus 1 times 4. I just wrote all the coefficient multiplied by the determinant. And then now you have 3 minus 4 plus 4. It's just 3. That's going to be the determinant of, so the determinant of this 4 by 4 matrix is just 3. Now that's how you can find the determinant for 3 by 3 matrix. And also all the, you can still apply the Cramer's rule here because we just found the determinant for this 4 by 4 matrix, and as I said, that is just like the generic steps that every time whatever the order you have for the matrix, here the order is 4th, so we are trying to find the 4th order determinant, and all we did was we took one element from column 1 and we ignored that column and that row, column and row for that element, and then we took the rest. So just like this one. So at the end we had 4 3 by 3 matrix, and again what we did was for each 3 by 3 matrix we did that. So we again to find the determinant of each 3 by 3 matrix we use 2 by 2 matrix. So at the end we just used a 2 by 2 matrix to find the determinant of a 3 by 3 matrix, and then we used the 3 by 3 matrix to find the determinant of 4 by 4 matrix. This is what you will always have when you have a higher order determinant. But at the the conclusion is you can always solve it. Just you have to go back. Like for n, you have to use n minus 1 order of determinant. For n minus 1 of one order matrix, you have to go n minus 2 order determinant. At the end, you probably will be able to do it directly when you have 2 by 2, just like the way we did here. Any question here? I know that you can solve the matrix. Still, you can solve all the matrix in calculator, but still you want to make sure that we understand the process. And also, when you see the question, it depends on the question, because some of the questions you may not be able to have the answer from the calculator. So it's always good to just know how to do the process and steps. So this is the end of section 8.5, because in section 8.5 all we covered was the Cramer's rule, and we tried to show you that how you can apply the Cramer's rule, how you can basically use the determinant and then apply the Cramer's rule using the determinant to solve the system of linear equations directly instead of going through the regular row operations for the matrices. But remember, at the same time, the Cramer's rules are applied in cases of this kind of matrix, which are like 2 by 2, 3 by 3, 4 by 4. So in that sense, still all the row operations that we have learned in section 8.1 are still valid when we don't have such matrix. We may not have like 4 by 4, it may be like 4 by 5, it may be like 2 by 3, maybe like something else. In general, you expect this when you are solving the system of linear equation because of this. Because what happens? Because when you see like 4 by 4, what does it indicate? It indicates that you have 4 variables here, right? You're trying to solve 4 variables, right? In general, what do we know? We know that if we have 4 variables, we at least need 4 equations. Otherwise, there is no way. It doesn't matter what you use. Doesn't matter whether you use algebra, you use matrix. There is no way you can solve that equation. Okay, so in that sense, Cramer's rules are still useful because in case of 4 equations, you will always have 4 lines. You see what I'm saying? So you will always end up with 4 by 4 when you have 4 variables. When you have 3 variables, you at least expect 3 equations. So that will be still like 3 by 3. But I'm saying if you have matrix for something else, not to solve the system of linear equations, something else, then probably you may not have these. But at this point, in our case, because all we tried was to solve the system of linear equations, so we know that, okay, we have 3 variables, we at least need 3 equations, 4 variables, at least 4. So we know that. So one more information that I just wanted to make sure that we know it. I probably talked it verbally, but I just wanted to make sure that we see this. Now, determinants, inconsistent and dependent system. Now, there are issues with some system of linear equations. Some system of linear equations may not have any solution. Okay, what does it mean that it doesn't have any solution? That's probably really interesting because the equations we see, those people already tried those equations, and when you see the equations, you already know that, okay, you assume that there are solutions, but there are equations in real life for which you do not have any solutions. What does it mean? It means that, for an example, you have a system of linear equations with 3 unknowns. Now, what does it mean? It means that there is no such x, y, and z for which all 3 equations can be satisfied. There are cases. Okay. In those cases, what happens? What happens is, let's say you have such a system of linear equation, and you are trying to solve it using Cramer's rule. Now, what you will see is the determinant will be 0, the d. Now, what happens when d becomes 0? Remember, when d becomes 0, what you are doing? You are basically, in Cramer's rule, you always try to remember the x. How do you find the x? You divide dx by d. Right? That was the general equation for when you are solving y is dy by d. Now, what happens if d is 0? You will get undefined, right? You get it undefined because you cannot divide anything by 0, right? So what happens is, when d is 0 and at least one of the determinants in the numerator is not 0. What do you mean by at least one? For an example, let's say we have how many determinants here? For a 3-order matrix, let's say for x, this is the equation. For y, this is the equation. For z, this is the equation. Now, if d is 0, you get d 0, but one of these or any of these dx, dy, and dz is not 0, is something else, then we assume that the system is inconsistent. That means system does not have any solution. That means there are no such x, y, and z's for which all equations of this system of linear equations can be satisfied. That's why you see the first one we wrote, the solution is null. That's a symbol of null set. But in another case, case 2, when everything is 0, for an example, all the d's are 0. Okay? These d's are 0. In addition to that, dx, dy, dz, everything is 0. If this happens, that means this kind of system has infinitely many solutions. What does it mean? It means that there are an infinite number of x, y, and z for which all three of these equations can be satisfied. Now, in that case, that's also difficult to find the solution because, when we are saying infinite, what does it mean? There are infinite number of solutions exist for this system of linear equations, and we cannot solve the system of linear equations in both of these cases. But we want to make sure that we understand the difference. In the first case, d is always 0 in both cases. In the first case, in addition to d, some of the dx, dy, or dz may be 0, but not all. but D must be 0. In second case, everything will be 0. All the determinants will be 0. Okay. So in first case, we are saying there is no solution. In the second case, there are infinitely many solutions. There are solutions, but they are infinite. Infinite number of x exist, infinite number of y exist, and infinite number of z exist. For those, all equations of this system of linear equations can be satisfied. So we don't have a in general, what we prefer or what we get in our equations so far, whatever matrices we tried in the class, we got a unique solution because we got exactly one x, exactly one y, and exactly one z. That exactly when you will have a solution. That means you have a unique solution. There is only one x, there is only one y, and there is only one z. For those, your system of linear equations can be solved. And that's the only time you will get the solution using the Cramer's rule. Unless, except, never. You will never get the solution. Whenever there is no solution, or whenever there are infinitely many solutions. But in general, just let me be clear, because since we are dealing with the linear equations, linear systems, all the equations, you see, probably you remember, except the trigonometric functions, because they have something else, because those are periodic functions. Except the trigonometric functions, all the algebraic equation gives you, let's say you have an equation of x to the power 2. The highest power of x is 2. Then you will have two solutions for x. Right? If the algebraic equation you have x to the power 3, and that is the highest power of the equation, that means you will have three solutions for that system of linear equations, or system of equations. It's not linear because it's a system of equations. But whenever we are dealing with this kind of issue here, we have all x, y, and z. I think you have noticed, right? So you have all x, y, and z. There is no x squared, there is no y squared, there is no z squared, because these are linear equations. So that means whenever you are trying to plot the graph in the graph paper, you will always have a straight line for these equations. For each of these equations, you will have a straight line. Okay. Now, if you really try to understand what really happens, why we say that, okay, there are a particular x, y, and z. Now what happens? Let's say you have three lines of equations. That means you basically have three different lines when you plot it. Right? Now what do we mean by the solution? By solution we mean that all those lines intersected at one single point. Three of the lines intersected. You see what I'm saying? All of the three lines intersected at one single point. In that point, that point is a coordinate, right? I'm saying in the graph, any point is a coordinate. X coordinate. So it has an x, it has a y, right? And that is the solution that you are getting here. That exactly is the solution. So that is basically nothing but the intersection point of all those lines. All those lines are intersecting in one point. Now, whenever we are saying there is no solution, what basically happens? That means they don't intersect. Just guess when they don't intersect. Only when they are parallel. If they are not parallel, they will always intersect. So basically, when you have no solution in the first case, so we are saying, okay, the system has no solution. That means all the lines are basically parallel. If you plot it, you see all the lines are parallel lines. That means they never intersect. And that's why they don't have solutions. I'm just, probably the book did not explain it in this way, but since you are introduced with the graph, the linear line, you already saw the plotting of the straight line. You have some understanding of the functions graph, so I'm just trying to give you a better idea that what exactly means and how everything, whatever we are doing is like correlated, okay? And also at the same time, remember the trigonometric functions are a little bit different with the trigonometric functions because they are periodic functions, so that even if they don't have x squared, you still get plenty of solutions for a single trigonometric functions because they are periodic. Within like 360 degree, every single values are repeated, or within one period, some of the values are repeated. So that's why the cases of the trigonometric functions are different. But other than that, everything is similar to this one. Any other question? Now, one more thing. When you think that system has infinitely many solutions, you know that, okay, system has one solution means all the lines are intersecting in one point, right? That point has x, y, and z, whatever, so that's the solution. When they are parallel, no solution because they do never intersect. Now, when you can have infinitely many solutions, technically that means they're intersecting more than one points, right? That's what exactly happening. They're intersecting more than one points, or probably infinite number of points, and that's why you have infinite number of solutions. Now, how it is possible that when you have, let's think about only two straight lines. Let's make it simple. Let's say you have two straight line, and they're intersecting more than one points. What happens? They're same line basically. They're exactly same line. Because you see, you can write the same equation in two different ways. Let's say you have one equation, x plus y equals to 3. You can write the same equations like 2x plus 2y equals to 6. You see what I'm saying? They're the same equations basically. You just multiply both sides by 2. Now when you have such situation, they are same line when you plot. Now when you have two equations and they are same line, look at this. When they are same line, they are intersecting in every single point. How many solutions they have? That's exactly what happens. So you know, I'm just trying to give you a bigger idea that what exactly happening behind. You solve it, okay, you see this, but what exactly happens in the graph? So that's how you'll know exactly. So you have the same equation. So let's say out of 3 equations, or whenever you have a system of linear equations with 3 equations, all the equations are same. You are solving in the matrix. At the end, you will see the system is inconsistent because they don't have solutions, or they are same line, they have infinitely many solutions. Okay, they are parallel line, no solution because they will never intersect. As long as they intersect, they will have a solution. Okay, that's exactly what is happening because we understand the linear functions. Now, this is the end of section 8.5. So officially, we covered the syllabus up to the last point. So any question up for this section? Any question about the matrix or about the chapter 8? Have you tried the homework for chapter 8 for 2 sections, 8.1 and 8.5? Okay. So let's stop the presentation right now, and also